Welcome back, Falcons. As we left off, we were looking at this contingency table, talking about conditional probabilities, and we were looking at birds given foreign. And what we can also do, and oftentimes is done when we're talking about probability, if we're going to just jump right back into it. Remember, we were looking at what's the probability of being foreign? Let's just highlight some of these pieces. Foreign, we have 498 over 663. That's our first probability. Our second probability is what's the probability of being a bird? Well, we have 253 birds divided by 663. What's the probability of being a bird that is foreign? Would be 175 over 663. We are consistently going back to the total of all of the animals when we're looking for this probability, for these one conditional things. If we're looking for what's the probability of foreign or bird, as we said before, 498 plus 253, take away the overlap, they're all over 663, which gives us 576. Excuse me about that. Now, if we're talking about foreign given bird, we know it's a bird, so it's not a reptile, it's not a mammal, it's not an amphibian. So when we know it's a bird, we know that the total has to be 253, or 253 out of 663. This is our denominator. This is the probability of being a bird. Well, where does this 175 out of 663 come from? Well, that's our overlap. That's the probability of being foreign and bird. And bird, if I'm abbreviating. And that's this formula, is we're looking at the more specific probability, 175 over 663, divided by the probability of being just a bird, or knowing that. What's the likelihood that that is the case? 253 over 663. Well, those denominators are the same, which allows me to look just in the specific subspace of birds. Likewise, if we flipped it, we can see that what's the probability that we are a bird given, remember, this means given, that they're foreign, is probability of foreign and bird divided by the probability of foreign, which would give us just 175. Again, that's our overlap. But in this case, we're looking at the foreign total, which gives me 498. So two ways of looking at the same type of contingency table. Or if we go back to our maintenance production office management company that we were dealing with, if one employee is chosen at random each month to get a good parking space, what's the probability that a maintenance or production worker is chosen? Well, if there's no overlap, we just add them. This, of course, assumes that no employee fills more than one position. And if that's the case, we again say that those two events are mutually exclusive or disjoint. Either word works. Okay, so let's see if we can apply this in a couple situations, because that's really what we can do. We can talk about examples, but these are the formulas that we're going to be bouncing back and forth between to figure out if independence, meaning one is not influenced by the other, is true. At our lovely little company, 36 people apply for a job. 20 are men, 16 are women. 8 of the men and 12 of the women have a PhD. It's pretty impressive. If one person is selected at random for an interview, find the probability that the one chosen is a woman or has a PhD. Okay, so we'll start. If we are just looking at this, we could simply say, we know we have 36 people that are applying. We know that 16 are women. So the probability that we are a woman is 16 out of 36. The probability that someone has a PhD, well, we said that 8 of the men and 12 of the women, or 20 total people, have PhDs. So we have 16 out of 36 plus 20 out of 36. We have double counted those women that have PhDs, which is what we need to subtract. And we said 12 of those. So 16 plus 20 minus 12 is 24 out of 36, or 2/3. Now, if we talk through those numbers, you can see where they came from, but it's better to visualize where these numbers are coming from. So again, a contingency table is also useful. Now, what do I mean? We want to know what's the probability of being a woman. 16 out of 36. We want to know what's the probability of having a PhD. 20 out of 36. Minus the overlap of women with PhDs. 12, let's do that in a different color. That is 12 out of 36. And with this OR statement, we take the two groups minus their overlap, because they're not mutually exclusive, and we end up with 2/3. Another example. On New Year's Eve, the probability that a person driving while intoxicated is 0.32, or 32% chance. The probability of a person having a driving accident is 9%. And the probability of a person having a driving accident while intoxicated is 6%. What is the probability a person driving while intoxicated or having a driving accident? So we want this OR statement or union. So we think, okay, probability of driving while intoxicated plus the probability of being in an accident minus the overlap. Or 0.32 plus 0.09, take away 0.06, gives us our 0.35. Straightforward enough. The next rule that we're going to add in to this list of things is the general multiplication rule. So when two events A and B are independent, there's that word again, independent, we can use the multiplication rule for independent events. Independence makes our probabilities easy. You just multiply. A and B is probability of A times the probability of B. However, when our events are not independent, or one is influenced by the other, oftentimes we use this word called replacement. This earlier multiplication rule does not work, and we need a general multiplication rule, just like we had a general addition rule. So we say the probability of A and B happening is the probability of A happening times the probability of B given A happening. Or we could say the probability of A and B is the probability of B times the probability of A given B. Notice these two letters match and they are opposites of each other, which is what we want. So I would really, really, really make a note of this general multiplication. If you're curious, why do you think, if we know that they're not independent, why it's just probability of A times the probability of B? I'll leave that thought exercise for you guys later. Okay, so going back to our bird problem. Notice this is not an OR statement anymore. This is an AND statement. So what's the probability we select a foreign and bird? The animal is foreign and it's a bird. Well, that would be 175 over 663. That is the overlap in the entire sample space. Now, where does that come from? We know the probability of being foreign is 498 over 663. And we know that they're not independent because there's some influence. We know probability of bird given foreign is 175 over 498. And hey, look, when we multiply these two, a foreign and bird, we see that we have 498 over 663 times 175 over 498. These two cancel out, and we're left with 175 over 663. So this table confirms the formula that we had before. Okay, one more time on independence. Independence of two events means that the outcome of one does not influence the probability of the other. Let me say that again. Independence of two events means that the outcome of one event does not influence the probability of the other. With our new notation for conditional probabilities, we can now formalize this definition. And in mathematics, we always love formalizing things. Events A and B are independent whenever the probability of B given A is equal to the probability of B. Or equivalently, A and B are independent whenever probability of A given B is equal to the probability of A happening. Otherwise, in other words, to determine if A and B are independent, determine if A given B is the same as A happening. If equal, the events are independent. If not equal, the events are not independent. Remember, most of our calculations are empirical and estimations of true population values. Thus, do not look for exactly equal values. If one is 0.51 and the other one is 0.49, in statistics, those are roughly equivalent. Or the funny way of saying it's good enough for government work. We are happy with close enough. Okay, I said this at the beginning with chapter 14, but it bears repeating. Just because events are independent does not mean the same thing that two events are disjoint. Disjoint events cannot be independent. Disjoint cannot be independent. We know that disjoint events have no outcomes in common. Knowing that one occurred means the other did not occur. Thus, the probability of the second occurring changed based on the fact that the first occurred. Thus, two events are most assuredly not independent. A common error is to confuse independence with disjoint and use the probability rules incorrectly. So a table that I suggest you guys keep on hand. We talk about mutually exclusive or disjoint. That means two events are mutually exclusive when their occurrence cannot be simultaneous, no overlap. Two things are independent when the occurrence of one event cannot control the occurrence of the other event. If we're talking about influence, occurrence of one event will result in the non-occurrence of the other. You're either in A or you're in B, you cannot be in both. With independence, when we're talking about influence, occurrence of one event will have no influence of the other occurrence. Think flip a coin, roll a die. What you get on the coin does not influence what you get on the die because they are independent of each other. There's no head 6 that you could get. Our formula to show two things are mutually exclusive is the intersection or probability of A and B happening is 0. Our formula for independence is the probability of A and B is the probability of A times the probability of B. If they're independent, we just multiply the probabilities. With a Venn diagram, we show no overlap. In independent events, by definition, we need that overlap because it goes to this idea that we have A and B over probability of B happening. Last couple slides for this video, and then we'll finish it up in part 3. Drawing without replacement. So think back to our deck of cards. Sampling without replacement means that once an individual is drawn, that data value does not go back into the population. This then changes the probability for the next selection, which means that they have to be dependent. Whenever we sample from a population, however, we sample without replacement, and this would suggest all sampling leads to dependent events. Howsoever, if the population is sufficiently large, and I'm going to highlight this, relative to the sample size, the difference in probabilities is negligible, and the events can be considered independent. However, when drawing from a small population, we need to take a note and adjust probabilities accordingly. So once your population is sufficiently large, then it's irrelevant what the sample size is, and we can roughly say they're independent. So good to know. In essence, drawing without replacement is just another instance of working with conditional probabilities. So we'll come back to this idea of replacement, wrap up what we want with probabilities, especially with this bifurcation or binomial distribution, and we will wrap up chapter 15, the first part, in part 3.